So good evening, everyone, once again. So today we are going to dive a bit more into some of the classical machine learning algorithms, which we looked at last week. We kind of just glossed over them, even though we went in depth to look at decision trees and random forests to understand what they actually mean, the principle of how they operate and how we could actually write our own manual algorithms if we had to write them ourselves for those. So it's something I'll still encourage everyone, right? Even though there are libraries that automate and simplify all those things for us now, but still try your hands a bit on them and try to understand them. So this week we will just quickly delve into support vector machines, k-nearest neighbor, and then we're going to look at clustering. Clustering is done with k-means. K-means is one of the ways of clustering. And then we have dbScan, which is a density-based spatial clustering of applications with noise. So that's a very long word. I'm sure they came up with the acronym first before the actual meaning. So clustering is a way of grouping you know, data points that have similarities together, and data points that, other data points that have similarities together in a separate group. So you just have multiple groups. And we'll show some kind of graphical illustration of these. And then we have what we call dimensionality reduction, where you have data set that has a large amounts of features, right? Features, so when we talk of dimensionality, is the number of features. But in most cases, you can only visualize two or three features, right? Um, if you have three features, then you visualize them in X, Y, Z. In fact, two features, X, Y, then Z would be the predicted outcome, right? Or the actual values. So once it becomes more than that, it becomes difficult to visualize. So dimensionality reduction helps to reduce from large high dimensional values to lower dimension that is easier to use either for visualization or for other things, right? Including trying to train, speeding up model training and so on. So let's start off with the support vector machines. So the support vectors machines basically just runs around a concept we call hyperplanes. So if you recall, when we have, because remember, essentially prediction is really about grouping, drawing a function that can predict or that groups data points into classes, especially if it is a classification problem, right? For now, let's even leave regression problems, but let's look at classification problems. So if you look at like this kind of data set here, right? You see the red and you see the blue. Now, a classification problem is, okay, we already have colors to tell us that's what we mean by target or label. So you have label data, right? So if you look at this as a typical data set, let me zoom in so that it will be easier to see this. So if you look at this, right, this data set, this is just a two-dimensional data set. So it's very easy to see it and to visualize it because it's just a two-dimensional data set. Once it becomes more than two-dimensional, it becomes a bit more difficult. So in this data set, you can see here the target, you have 0 and you have 1. So what we are trying to classify as 0, that is false, is red. We give a red color. What we want to classify as true, we give it a blue color. So if you look at this, right, the best kind of solution, if you look at this, the question will be, do we even have the best solution for this problem? The best solution will be a line, a function that draws a line that cleanly separates the red from the blue. That's really what that prediction is about, or that's what training. Training is you start with a model. So in this case, you cannot use a linear equation here because a linear equation is just totally inadequate. So remember, if we are doing linear regression, what we would have tried to do is look for a line, for clustering or for other kinds of problems anyway, a prediction problem. What you are trying to do is, what is the line? What line can I come up with that will separate these two sets of predictions, right? So normally, if it was a linear equation, so let's say we are just doing a linear equation. You are trying to draw a line, right? You are trying to find a line that will separate this thing into cleanly separate them into the two categories. It's very difficult, and the reason why it's difficult is because these things are scattered in a way that is non-linear. You really cannot come up with a straight line. Maybe the best straight line you can come up with is this, something like this, right? So if you came up with this straight line as a way to characterize, this, let me make a bigger straight line. So you came up with this straight line. What you will notice first of all is that this straight line is not adequate because it's not cleanly separating the blues from the reds, as you can see, right? It's not cleanly separating. You will definitely see that you have a bunch of blues here, right? You have a bunch of blues here. Okay, and then you have a bunch of reds on this side. So you don't have a very clean, separation. So you have things that are carrying over, right? In fact, you even see some that are overlapping, like this red here. How would you even separate? What kind of, curve would you draw to separate this red out? So these are, if we were calculating the cost function of this line, these reds that are on this other side, right, would be the ones that will give you a high cost function. And these blues that are on this side are the ones that will give you the high cost function. So the blues on this side and the reds on this side. Okay. So now you could do a better job if you were to use a polynomial function. With a polynomial function, you are not drawing a straight line, you are drawing a curve, and that curve can have any number of, shapes. So you could, for example, start off with a curve that starts off here. Okay, I'm still having this as a straight line. So let me go look for a curve. So I want to do a curve, right? So that curve can start off from here, kind of try to cut around it. Now, at this point, the question is, if you probably want to follow all the blues up there, that might be overfitting, right? But maybe you can do something like this. And then if you really look at it, a lot of the blues that are on this side are like outliers. So this is probably the real blue line. Okay, so you would draw something like that. But even with this, you can already see that you really can't capture everything. You still have these reds here that are, on the blue side, right? And then you still have these blues here that are on the red side. So even with a polynomial function, right, you really cannot get a perfect zero. That's why for these kinds of problems, no matter how well you train your model, no matter how good the model is, the error can never be zero because there will always be, outliers and noise, right? Noise. These outliers may actually be real outliers, or they might be from noisy data, right? Data that for some reason, you got the thing it gets it wrong just out of noise. So, but this is the whole idea of classification, right? So when you now go away from the realm of a linear equation where you are just drawing a single straight line and you start trying to do something more fancy, right? That's where we now start talking about support vector machines. Now, in the context of a two-dimensional, space like this, where you are just having feature one and feature two, right? So you have two features. The feature one is on the x-axis and feature two is on the y-axis. And then the label, we use the color to determine the y hat, the actual value we are predicting. And then we use this line, which is a boundary, right? So we use the line, which is a boundary to represent our prediction, right? When you use a line as a boundary to represent our prediction, that line on a two-dimensional space, of course, is called the line, right? But when you go to a three-dimensional space, it is no more a line that separates. It is what we call a plane. So a plane now separates between, um, you know, the values that the different colors, the different blue and red. So if we scroll up now and look at this, you now see that you still have this same blue and red, right? That was down here. You now see you have it up here. You now see that this is a two-dimensional plane. But this two-dimensional plane, right, is not enough because the data is not actually two-dimensional. There may be other things, right? So in a three-dimensional space, you may find that it's not flat, like it's not just the X and the Y or the X1 and the X2, but there's also an X3 in this third dimension, in this Z dimension, right? That separates the vertical separation. It is now with that vertical separation that you can now, give additional separation. So that's the third dimension. And you can have others, a fourth dimension, a fifth dimension, and so on, which we cannot really visualize because the human mind has only been trained to visualize three dimensions. So looking at that now, what you can then say is that um, with support vector machines, we now are dealing with planes because support vector machines is designed to allow you to do separation, of these classes based on more complicated lines and surfaces, what we call hyperplanes. A hyperplane is basically a plane that is in multiple dimensions. That's why you use hyper. A plane is a surface in two dimensions, right? Like this one that is down here. But a hyperplane will now have a third dimension and a fourth dimension. And these hyperplanes are combined. So I'm going to play a video quickly that is going to show us, right, how these support vector machines, in the hyperplanes, how they come about, So this video doesn't have any sound, so don't worry about the sound, but just check out, what happens. So this is SVM. We use what we call a kernel. So here, first of all, you have blue and red dots, and you can see that they are not linearly separable. So you even have, in this case, they even try to separate with a circle. So the circle is the shape, or is the boundary that we want to use to separate because all the blues are kind of surrounded by the reds. So what it means that by not linearly separable is you cannot use a straight line or a linear equation, right? You know, even if it is a multivariable linear equation, you cannot use that to separate it. You actually need to have this circle. So they are not linearly separable. But when you use what we call a polynomial kernel, so in support vector machines, they use what we call kernels. A kernel is essentially a kind of, let's say, algorithm or a plane, a function. It's basically a function that you will use, right? That it will be able to do the classification, right? So we'll talk about that more. Now, this kernel can have multiple dimensions. So they use a kernel And using a polynomial kernel, they can be linearly separated in 3D space. So we now switch to a 3D space. This thing is going to show you how that happens. So this is where I took that screenshot from. So you see this plane now, it is a two-dimensional plane. But when you add a third dimension, you see how everything comes up. But even here, you'll be wondering, how do I separate the blues from the reds? So you now see that an additional plane comes in. That plane here is the hyperplane. This thing that you're seeing in purple. It's a plane that is in 3D. It's in 3 dimensions. It cuts through this because already this two-dimensional space we're seeing that is 2 dimensional, actually 3 dimensional. In the 3 dimensional space, you can see it has a valley, the point of minima, right? So with this plane, it is now able to separate, and that's where this circle comes from. This circle actually, this circle we saw initially comes from a hyperplane cutting through the actual plane or space of this. So what we are seeing in 2 dimension is not the real thing. It's just a summarized version. But when you take a plane and you cut it, then you now end up with this thing, which is a circle, right? And that's really just what it is. It's just a circle, right? That's what it is. So you will see this as you know, the result of that. Now, um, so let's look at how all of this works, right? So we are going to um, take a look at um, the Jupyter notebook that kind of tries to explain all of this very, very clearly. So if you look very, very clearly, you'll see um, some of the key concepts that you will have to understand is what we call a hyperplane, which is the decision boundary that separates the classes. Okay. Then the margin is the distance between the boundary and the closest point. So if you recall that there is always this thing which you will see, the closest point, when you draw that boundary, there will be points that will be very close to it, right? Um, those points are the ones that matter most, right? The points that are far away from that decision boundary are not, they don't really matter because you can adjust the decision boundary, to a certain extent without those points without the points that are far away, without affecting the classification of the points that are far away, right? But for the points that are close, okay, you it becomes very, very important. So again, let me use another video to try to explain, what I'm saying. So if you look at this, you see that for um, this is a good example. Like if you start off with, let's say you start off with, you have this whole bunch of objects, right? And the you start off with this, right? These are this is a simple decision boundary, right? You can see a simple straight line will separate the reds from the blues. So that's a very simple one. But at some point, right, if you look at it from a two-dimensional, you see this has been flipped into from 2 dimensional into 3 dimensional. That single straight line that we had before now becomes a plane, right? So it's now a plane. And then that plane that we are seeing, okay, it becomes much easier, for you to separate because you can wrap this plane around. So if you continue to look at this, you see again, it's back to two-dimensional, and you can see how it how easy it is to adjust. Essentially, what this is saying is that this plane has a lot of room for adjustment. Not only a single plane can do this classification, there are potentially like three, four, five different solutions. In fact, there are infinite number of solutions within a particular range, right? That range starts from, if you look at it, from where we have, let me draw some lines here. So that range starts from here, right? From this line, okay, let me use a different color. From this line, you can use this line to separate, right? It will still separate these two classes cleanly. And then to this other line, which can also, almost, maybe not perfectly. So you have this range. This range here is the range of flexibility that you have, you know. So that means it's easy to classify this one because, you can, between this line and this, there's an infinite number of lines that you can draw, right? That would still successfully, you know, I don't know if you get what I'm trying to draw. That will still successfully classify those 2 points. But there are situations where you could find yourself where, yeah, so this, this space, right? This gap that this line has. Again, okay, I did show one thing that you can rotate the thing, but you can also, there's also the um this translational distance that you can still move this line and you still have proper classification. Even if this line were to move all the way to this point, right? If this line were to move all the way to this point, it is still a good line. Even if we were to move all the way to this point, still a good line. So that is again the flexibility in a linear direction, right? The other one was flexibility in an angular direction. So this space here is kind of the boundary, right? That margin, right? So that's what we call the boundary. Now, the vectors that exist at that boundary is what we call the support vectors, right? And so the support vector machine is basically a way of, identifying all the support vectors, right, that separate, that act at that decision boundary, what we call the decision boundary that separates, one from the other. Now it's easy to do this with sklearn. So you can already see with sklearn, you just bring the SVC class, which is the support vector, class, and then you can use that to basically implement. Now let's go back to our thing. So the distance between the boundary and the closest points, that's the margin, right? So the support vectors are the critical points. Remember, a vector is a list of numbers. So the critical points in that plane that define the boundary, the point at which you are able to separate and classify, right? That forms what we call the support vectors. And then we have what we call hard and soft margin. So the hard margin is where you don't have any errors. You draw that line across, or whether it's a straight line or a curved line, right? You draw that line across. I don't have any errors. In other words, you don't have the blues, leaking over or crossing over into the red side of that boundary and so on, right? That's a hard boundary. So it doesn't allow any errors. But a soft boundary is the one that may allow errors based on what we call a penalty, given the value C. So what this means is that we can allow a certain amount of overlap, right, based on the penalty. So why does SVM work very well? It's very good in high dimensional spaces. So spaces where you have lots of dimensions, right? Multi-dimensional spaces, multi-dimensional data, right? It's robust and it gives clear separation, right? and you can model nonlinear boundaries using kernels. So a nonlinear boundaries, if you remember the first graphic that I showed, where the boundary is not linear, but when you use kernels, right, you're able to achieve that. So you have several kernels that I used, right? For nonlinear support vector machines, you use kernels to achieve that. And as you can see, if you remember the first graphic I showed, when you apply a plane in a hyperplane, right? In if well, we apply a straight plane, right, across a hyperplane, and we ended up with something that looked like a circle, right? That's what that trick does. That's what that kernel trick does. So the common kernels that you can use, you have what we call the linear kernel, right? You have the polynomial kernel, you have the Gaussian or RBF kernel, and then you have the sigmoid kernel, which we talked about sigmoid function some time ago, right? So normally the idea is that you want to maximize the margin, right? You maximize the margin by minimizing this value. So the value that you are minimizing is half of omega or W squared, right? Plus C sum of epsilon I. W squared obviously are the parameters. So you want to minimize that. C is a constant. So that C is the penalty, right? If you remember when we were talking about penalty C. So the decision boundary depends only on the support vectors. So remember, the support vectors are those lines that determine the point of separation, the critical point of separation between the classes, right? Between the reds and the blues, for example. So those critical points in that boundary that define the boundary, and I think I showed you when I said you can, in some situations, the boundary has flexibility to adjust, but there's a certain point to which you adjust the boundary and you can't go beyond. Those are the critical points, right? So the critical points that define the boundary. Um, so typically, right, um, the pros and cons of support vector machines. Pro is that it's powerful when you have a few examples. It handles both linear and nonlinear problems and is effective in high dimensional feature spaces. So if you have high dimensional data, but the number of data points are few, right? You can use um, support vector machines. The problem with support vector machines is that when you start having large data sets that has a lot of data points, then it becomes very slow and computationally heavy because of how the kernels are calculated, right? So it also needs careful tuning of the penalty C and the Y and the kernel, right? And it is not as easy to interpret. So let's just look at it a bit more in depth. So these are when we talk about hyperplanes, right? The hyperplane, like we said, in a two-dimensional space, right? The hyperplane is just the line, like we showed, a single line that separates the two categories or two classes that you are trying to categorize, right? In a three-dimensional space, right? That line becomes what? A plane, like we saw, in the second video, where, it basically just flips the line and the line became, a space, sorry, a plane. So that happens. That's basically the correlation, right? And this is it. So in a three-dimensional, this line becomes a plane, right? In a three-dimensional space. But beyond three-dimensional spaces, right? Four-dimensional, five-dimensional, and so on, right? That single line that is a plane or a curved plane or whatever becomes what we call a hyperplane, right? So For linearly separable data, you want to find the optimal hyperplane. So basically, you can have multiple planes or multiple hyperplanes, just like you could have multiple planes, right? That separate this data. So like I was showing with the lines, even in this context of planes, you can see that there are so many ways you can bend around this plane, right? And you'll still be able to properly um, classify the data. But the only challenge you will have is once the data becomes a lot, like what we had, where I was showing you the first example, then you will now have a situation where the number of possible hyperplanes that can properly fit the data and classify it becomes reduced. The more the data, the more complex the data, the more the data points interact, the more difficult it is for you to find that. So that's that concept. Then the margin, of course, distance from the hyperplane to the closest data point. So the SVM approach is to maximize the margin, right? Because once you maximize the margin, in other words, you get a decision boundary that maximizes the margin and increases the space on both sides of that decision boundary or the support vector. Then that allows for more generalization because it means you can get more points in. Then points that lie on the margin of boundaries, on the margin boundaries are called support vectors, like we've said already. So the optimal hyperplane is the one with the maximum margin. So the solution to support vector machine is also an optimization problem. And what you're trying to optimize is to maximize the margin. So what you would do is you are essentially going to calculate the margin, when for each support vector, right? For each line or each boundary, right? For each support vector that determines the boundary, you calculate the margin, right? And you eventually find the support vector that gives you the highest margin. That is a simple approach. So support vectors are the critical training samples that determine the hyperplane. So essentially, like we said, the support vector are the points that lie on the margin boundaries. When we say points that lie on the margin boundaries, right? What we are effectively saying is that when you draw a line like this, right, there are some of these data points that are close to the boundary. In fact, there are data points that will lie on the boundary, right? So for those data points that lie on the boundary, either lying a bit to one side or a bit to the other side, you don't have any flexibility, to adjust the boundary at that point. Because if you adjust the boundary at that point, then you are effectively going to end up, you know, misclassifying that data point that is on that boundary. Okay. So that's that data point on that boundary is one of the elements, one of the data points in your support vector. So when we say support vector is a vector of those points, those data points that lie on the boundary. Okay. So those are what we call that's what when we say critical training samples, those are samples, and that's what determines the hyperplane because with that, it determines the orientation of a hyperplane. It also determines the position of a hyperplane. So again, remember, you can adjust the hyperplane anyhow, right, to fit the data. But the actual specific places where you will place, the hyperplane, you cannot go beyond the training samples that are on that hyperplane. Otherwise, like I say, you misclassify. So now, when we say soft versus hard margin, the hard margin means that you are assuming that the two data classes are perfectly separable. In other words, you have a perfect separation between the reds and the blues. You can't have some of the blues, uh, flowing or overlapping or leaking into the reds. And you can't have some of the reds leaking into the blues. That's basically what that statement means. So, that's a hard margin. So because you assume a perfect separability, you don't allow any misclassification. So if your boundary, your hyperplane boundary kind of allow some red to, overlap or leak over into the blue side, that is considered an error. So that misclassification is not allowed. And because of that, so the hard margin SVM is always sensitive to noise and outliers, because those are the ones that tend to, overlap into the wrong side of the boundary. The soft margin allows for misclassified points. So you allow a certain amount of misclassification, right? And that amount that you allow is determined by this penalty parameter C. So what we are saying is that I should not allow more than this C. C is a constant, but it determines how much of a misclassification that you allow. So you use this to be able to balance maximizing the margin while minimizing classification error. So in a soft margin, there's always going to be a bit of cost, a bit of error. While in a hard margin, no error is allowed. It should be zero. Error should be zero. In other words, no misclassification. But soft margin, yeah, you can have a bit of that. And the C parameter now controls the tolerance for errors. So a large C will mean that you have low tolerance, right? Strict boundaries. But a small c means that you have high tolerance, okay? So those are the concepts. Now, how do you do nonlinear classification? So remember, with linear classification, it's very simple. You simply draw a line, a straight line, a plane, or a line, or a hyperplane that will easily separate the blues from the reds, right? The ones from the zeros. But when you now have a lot of, you know, more complex distribution of data, right? Classification problems that are a bit more complex, then you can't really use linear boundaries. The linear boundary is not enough, like we showed here in the first video, which I can still bring up that first video, right? You really can't do that with a linear boundary. So what you can do is to bring the kernel. So the kernel is a way of you kind of modifying, right? Modifying that linear boundary to allow it to do non-linear, right? So you can see that this particular set of elements required a circle, right? It required a circle. But we were able to achieve it by basically projecting this data into a three-dimensional space, right? And then after projecting into three-dimensional space, we apply a plane. This plane is actually a linear plane. So we now apply a linear plane into the three-dimensional projection of this space. So what I mean by projection is this. If you look at this data, you will see that everything on the floor in this case is a two-dimensional linear, um, two-dimensional projection, right? But it's not the real nature of the data, right? So for example, this point here that I'm pointing at has a matching point up here, right? That's a projection. So a projection is basically projecting it. As the name, just think of it like a projector, right? With a projector, what you are essentially doing is that you are taking something that is on a projector and you are sending it to the screen. So it moves a certain distance. So everything on the floor here projects to a corresponding point in space. And that's really what's happening. So you have the blue. So by the time you do a projection of all of this, in and include its actual z-dimensional position, right? You now see that it is no more a flat place where you say, okay, it's flat, I need a circle, but rather it is a curved hyperplane, right? And then in this curved hyperplane, we can then introduce the this simple plane, which is a two-dimensional, or yeah, it's a plane. It's a three-dimensional. It's a plane in a three-dimensional space, and it cuts through this hyperplane, at this point. And then when you project this point of, separation back down into the two-dimensional space, you now get that circle that we saw. So that is really that's really what it is. You now get that circle. This circle is just a projection. Think of it as a projection of this line. This line that I drew to cut here is a projection of that line down here, right? It becomes a circle. So this is the principle of the kernels, right? In support vector machines. That's really what the kernels are doing. So like we said, we have different kinds of kernels. You have a linear kernel, like that one was a linear kernel because it gives us a a plane that is a straight, flat plane, right? So with that kernel, we're able to cut the hyperplane and we're able to get this. So a linear kernel is best for linearly separable data. So what we mean by linearly separable data is data that you can use a single line to separate it when you have put in that space, in that three-dimensional or hyperdimensional space, you can separate it. Polynomial kernel is a kernel that you can have up to a degree D, right? Basically, polynomial, like I said last time, is when you have, in those days, a polynomial is, well, still now, a polynomial is any function where the power of x is higher than 1, right? So you have x power 2, right? X squared plus 2x plus 1, or you can have x cubed, x to the power 3 plus 2x squared plus x plus 1, and so on, right? So that's a polynomial equation. So you have kernels that also have up to that nth degree or nth degree or nth order. Then we have what we call a Gaussian kernel. A Gaussian kernel uses this exponential equation, e raised to the power minus gamma times the second order norm of x minus x1. This second order norm is basically the same thing as what we use for mean square error. That is x minus x prime squared, right? So this Gaussian kernel is what is most often used because it's very flexible and it can handle any number of complex nonlinear, problems. Then we have the last one, which is a sigmoid kernel. The sigmoid kernel uses a sigmoid equation. If you actually look at this tan equation approximates that our sigmoid equation, which we were doing that time when we were talking about logistic regression. So with that, with the sigmoid kernel, you can also achieve some good separation for data that mixes up a lot, right? So yeah, so when you are using SVM, support vector machines for regression, right? These are the key things that you will think about. It's called support vector regression, SVR. So you have to create a function that you fit within an epsilon tube around the data. So an epsilon tube, epsilon is an error. So you are basically going to define an error margin around that data. And then only points outside of that tube become support vector. So remember we talked about margin already. So the margin is the distance between the classification boundary or the decision boundary and the data that is closest to it, right? Or the data in the support vector, right? So for regression, you only use points outside of this tube to become support vectors. So it uses a similar concept of margin and kernels, right? So you can use SVMs for regression as well. So these are some of the maths, right? And I'm going to just go through them quickly. You don't need to overflog these maths, right? But for any separable set of data, right? This is what it solves, right? And this is SVM in the most basic form, right? What we call primal form, the linear kernel, right? Linear SVM that uses a linear kernel. So the first thing is that you want to minimize W for every B, right? And W is basically the margin, right? So remember, we're trying to minimize the margin. Um, we're trying to maximize the margin actually. So we minimize the inverse of that. So you have half of W squared, right? Subject to Yi being Yi is the parameter, sorry, Yi is the for each Y, right? W is a parameter times X plus B greater than 1. Then with a soft margin, what you will do is you will add the C, which is the um the safety factor that we have added, the tolerance, right? Or the penalty. So you want to use that penalty and you calculate the error that you allow. So like we said, if the penalty is large, it means we want to allow more. Sorry, we want to allow less, right? If the penalty is more, we want to allow less. If the penalty is less, we want to allow more misclassifications. So this error is a measure of the misclassifications, right? So you use this penalty as a factor. And you want to minimize that. So if the penalty is higher, that means you can allow more of the sorry, you can only have less of this, but if the C is less, then you can have more of this. So they are kind of complementary. So you are minimizing this, right? With a soft margin, you add that factor for allowed misclassification, but you are still going to do this. This is the function for it, right? Yi is omega or W dot xi, where W is the parameter that you use in the linear equation for the linear kernel. And you're saying that this function must be greater than or equal to 1 minus the epsilon, which is the error that is allowed, the misclassification that is allowed. So that's the primal form linear. And then for the dual, you have what we call Lagrange multipliers, and it's applied for the kernel. So this is kind of a bit more complicated stuff, right? Which you don't need to worry about. But the Lagrange multiplier is alpha. So you want to maximize this sum of alpha for each data point minus half of alpha I times alpha j yj k, which is a constant. K is a function of x1, xi, xj, where xi, xj are the ij, basically the different features, you know, the the you could say these are the data points that make up a support vector. So anyway, you can we can just get through the maths, but the most important thing here is to understand that the kernels, what kernel do you use, right? What kernel do you use when you are using SVMs? So advantage of SVMs are effective in high dimensional spaces, like we said already. It's robust to overfitting when the number of features is large. It's very good when you have a large number of X values of features, right? It works well when you have clear margins of separation. It's flexible by adding kernel functions, and it can handle both linear and nonlinear classification. But for limitations, it's not very ideal for large data set, like we've said, because training it is expensive. Then it's difficult to tune the hyperparameters, right? The tolerance, the lambda, the kernel choice, the gamma kernel choice, less interpretable compared to simpler model. I think we've gone through all of this already. So you can see the hyperparameters that you are tuning. The C is a penalty for misclassification or tolerance. The gamma is a kernel width, right, for RBF. And then you have degree for polynomial kernels, and then the kernel itself that you choose, which is whether it's linear, polynomial, RBF, or sigmoid. So we'll go into some few examples of maybe one or two data sets and how you can just run it through with SVM, right? Um, so let's say let's see. I'm going to bring up simple data set. Okay, so we have some data from um scikit-learn, right? So sklearn, we are going to get some data from sklearn, which we can use to do some of this classification. So let's start with some very simple example. All right, let's see. Um, so we can start with very simple example. X equals simple 0, right? 1, 2, 3. And then Y equals 0, 1, 2, 3, right? So if we wanted to plot this, well, we can. This is a multi-class, by the way. What we mean by multi-class is you have let's use a single class. So instead of multi-class, let's say 0101. So this is a simple single class. If we wanted to plot this, right, we can just plot X and Y. Okay, we can just plot X and Y, but I want to go to something a bit more interesting. So we have some data points and we have uh, okay, so this is X and Y, right? And I want to plot I want to plot this to show you a single simple scatter plot, right? So if the idea is if Y is 0, we'll use the red color. If X is 0, sorry, if Y is 0, we use the red color. If Y is 1, we use the blue color. Okay. So so let's import matplotlib first. Okay. So Okay, so one simple way to do this is um let me just bring this code here. So we take each, basically we unzip, right? And unzip, zip. Okay, let me keep it this way so that it's easy for others to understand. Then we can just plot. So okay. All right. So so here we have red and we have yellow and black. So we have these four data points, right, which we have extracted, and um, this is one of those difficult ones that is difficult to draw a decision boundary. So okay, let me change this a little bit. 0110. Let me see what 0110 does. Okay, so this is how 0110 looks like. Dot big size figure. Okay, 5 and 3. Okay, so this is easy to draw a decision boundary. Like you can draw any number of lines here, right? Um, you can, you can draw a line here, between here and here, right? So it's very easy to actually train this. So we will now see how this trains with a simple um SVM, right? It's very simple to do that. So we'll use sklearn to do this. Uh, so it's really easy with sklearn. So you just import, right? You import SVC, right? We're not going to do any pipelining or anything. We just import SVC, which is the support vector classifier, right? So you have SVC, you have SVR, which is regressor. Then you 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 class function, right? Um, is SVC. Then you choose a kernel. So you can see you choose a linear kernel because this is very simple for you to classify. You choose a linear kernel. Then you run fit. That's all. Then when you run fit, then what I'll do is after you run fit, you now get the X and Y values, right? Or you get the decision function. And then you can print it or plot it, right? So let's show you how the decision function looks like. Decision function. So um, the decision function basically is the function that will give you the that decision boundary. That's why it's called decision function. So decision function will give you a decision boundary. So you can pass in, let's say the x, right? You can pass in the x, and then you see what you get. So even though it's giving us minus 1, 1, 1, minus 1, but it is close to what we want because what we want was 0, 1, 1, 0, right? The only thing is that here it is mapping minus 1. It has basically its own understanding, or what it gives you as minus 1 is the other class, the opposite class, the negative class, right? And and this is it. Now, how can we plot this decision function? So it's very simple. Um, let me let me go get a more complicated data set. Okay, so I want to show you data sets that we can get. So we have a whole lot of interesting data sets that we can use. But this is one that we can use for, but this is 2D data sets that we can use. So you can go check this. I'm going to share this link, right? So we are going to, we're going to pull this in and then see, or maybe I'll leave this because I don't have a lot of time. I want to move on to the next one, but maybe I'll share this so that we can do, you can work on it, right? Um, on your own later on. So typically, if you want to plot the decision boundary, right? Okay, you would first of all, um, because you are doing two values of X and two values of Y, you have to basically generate all the data points for X and, well, all the data points for X, right, in this two-dimensional space and combine them together and then use that to calculate corresponding Ys, and then you can plot a line. So that's typically how you would do if you want to plot it, right? So let's see how you can do that. So let's say x mean y x max equals we start x, we take the first of x, which is um the first column of x minus 1, and then you take the first column of x, the max, again plus 1. So basically Then you take y mean, y max. Um, Remember, you actually what we are calling x mean and x max, y mean and y max is just for the sake of plotting the graph. It's not the actual value of y. What you're actually doing is that we are plotting x1 on the x-axis and x2 on the y-axis. So maybe we shouldn't be calling it that to avoid confusion. So there should be x2 mean and x2 max. So -1. So same thing. This is 1 plus 1. Okay. So you take this and then you do what we call a mesh grid, basically, right? And so you can get the values xx1, xx2 equals np numpy. You use numpy mesh grid. So instead of using a range, which is what this is suggesting for me, I want to use linear space. So lin space. So want the values to start from x1 mean to x1 max and want 300 points, 300 data points. And then we also want a linear space from x2 mean to x2 max. And I also want 300. The range would have done the same thing though, but let's just go with this. So that gives us two vectors that are spread across the this thing, across the space that we want to plot the graph. Then we now predict. So we now use these values, right? And we use that we pass it the xx1 ravel and xx2 ravel will kind of expand them and pull them together. So and then it gives you something that is similar to what we have, but it will give you more data points, right? And that is what we will take, reshape, and then we will plot. So 5, 3 will now plot a contour plot, xx1, xx2, which are the two axes of x and y, and well, x1 and x2, the two axes, right? And then the z, which is the predicted values that you predict from the um SVC model that you have trained. So remember, we trained the SVC model, support vector classifier. So we've already trained it. We are now trying to use this classifier to predict values based on some random values that we pick to see its decision boundary. That's essentially what we are doing here. So we use a contour function, then we can still plot a scatter of the x and y. So we do a contour function. The contour function is going to plot a plane, like a 3D map of what the support vector machine has predicted, right? While and then CMap is a color map, so we are basically using a separate color map. But I can look at another way of doing this. Then the plot.scatter is plotting the actual data points. So this is kind of a way for you to do that. And yes, I need to import NumPy as well. So I think I did that already. Um, hmm. List indices. Okay, this wasn't a numpy list, so that's the issue. Okay, I was dealing with normal lists, so let's make this np dot array. Let's make this numpy arrays. Okay, so we can just run everything. Okay, so you can see that the decision boundary for this was at around 1.5. So it has separated this up and down. Now, interestingly, if I were to switch this and say 0, 1, 0, 1, which I had before, instead of 0, 1, 1, 0, if I put 0, 1, 0, 1, let's see what happens now. Well, it actually doesn't do a good job because, like we say, a linear classifier will not do a good job. You can see there's overlap here. Um, Now let's try using something, much better than linear. In this difficult, this is the kind of problem that you say, okay, how for us to classify this, we would need to draw like a circle or something here, right? So let's just see, let's try all the kernels. So the different kernels that we can have, we can try polynomial. We have linear, polynomial, RBF, sigmoid. So let's start with, we've done linear already. Let's try polynomial. Now, it might ask for a bit of additional information. So, polynomial. Okay. So it's saying polynomial. Okay. So with polynomial, you can see with polynomial, we now have a much better, you can see it does a better job of separating these two using two decision. It's not actually two decision boundaries, right? But it's just that in the space that we have, it is it has kind of when you go to the hyperplane space, this is actually still a plane cutting it, but it cuts it and the projection now looks this way. So that's polynomial. Let's try a RBF. So RBF is going to give us another interesting one, but it still does a decision boundary, right? So sometimes you need to ask yourself, okay, what is the best option? And let's try sigmoid. So with sigmoid didn't do very well because it failed at this point. It failed at this point. So this gives you an idea of what SVMs do. This is actually just very few data points, but it gives you an idea of what SVM does. Okay, so I'm going to put this data set here, and we will I would like you to go take a look at this. There are actually a bunch of them here, so you can go check out this, and let's see which one will be. You can check this out and just use these data sets to um, try out your SVM problems. I'm going to recommend that we um, do a bit of work on your own, right? So SVM data sets. Do a bit of work on your own and try to practice, at least so that you master, at least you understand the behavior. Right. Now let's move on to just look at others. I'm not going to go into so much detail. I have another bunch of Jupyter notebooks. So we've looked at support vector machines. The next one we will look at is the we call it, let's see, let me bring this back here. So if you look at this, what we call k-means clustering. So k-means clustering is a clustering algorithm, right? So what does a clustering algorithm do? It basically allows you to sorry, k nearest neighbor. It's a classifier, not clustering. K means clustering. We'll get to it next. So k nearest neighbor is another way of doing um, binary or multi-class, multi-category classification, right? So it's based on a majority level of nearby samples. It's simple, it's interpretable. That's one good thing with the k-means. And the performance depends on distance metric and value of k. So examples of where you use k nearest neighbor is the recommender systems, and you also use them for pattern recognition. So let's look at that. Um, k nearest neighbor. So for k nearest neighbor, like we said, it's instance based, it's supervised learning algorithm, just like the SVM. It's used for classification and regression, and it predicts an output based on the majority class. So, or average value. If it is a regression problem, use the average value. If it is a classification problem, use the majority class of the k nearest points. So effectively, what you are doing is that you take a point, you find the k nearest points around that data point. Nearest in terms of distance. How do you calculate the distance? You use what we call a Euclidean distance, right? So Euclidean distance. So I'm going to see how I can explain this, right? So let's assume that you have, let me make some sketches as well. So let's assume that you have some data points, or in fact, let's just take a single data point first. So you have a single data point, right? Somewhere. Okay, so this single data point um, is surrounded by a bunch of other data points, right? So let's first of all draw X and Y axis. So we use a blue color. So you have the X and you have the Y axis. Okay. Then you now have data points. So a bunch of data points. So you have data points, you know. Okay, now. So when you want to do classification, right? The k nearest neighbor is k is a hyperparameter that you provide. And then the distance metric. So let's say we want to start with a particular data point, maybe this one, right? We are now going to calculate the k nearest neighbors to this. And what are the k nearest neighbors? So let's assume that k is what? Maybe k is 4. Let's just take k. So k equals to 4. So we take a value of k to be 4. So if we take a value of k to be 4, so what we are doing now is we want to find the 4 nearest neighbors to these data points. Okay, so what are the 4 nearest neighbors? It would, oh, this is a really big arrow. Okay, so the 4 nearest neighbors, we'll find the 4 nearest neighbors. Um, I need a really tiny this thing. Okay, so these are the 4 nearest neighbors. This is neighbor 1. Um, this one is clear that it's near. So maybe this guy is the second nearest neighbor. This is the third nearest neighbor. And this one is far, this one is far, this one is, these three look like they are really close. So maybe this guy is the fourth. So those are the k nearest neighbors, like the four nearest neighbors. So of course, this is based on a Euclidean distance. Euclidean distance, there's a formula for calculating it, but on a two-dimensional plane, right, the Euclidean distance basically reduces to um Pythagoras theorem, basically, which is, the distance d squared equals x squared plus y squared, right? So you get the d as the square root of x squared plus y squared. That's it, right? But on a multidimensional plane, right, there is an equation for that, which, like I said, on two dimensions, it reduces to that. So when we now find the k nearest neighbors, okay, then what we now do is to predict the output based, we say that, okay, the class of this, we are going to predict the class of that data point by calculating the class of the highest, right? Like, okay, so let me, let me, let me, improve this a little bit. The highest number, the class of the highest number of data points among the k nearest neighbors. That's really what it is. So I should have completed this by adding the red classes. So I only did the blues. So let's do the reds, right? So let's assume we have a bunch of reds as well. So I need to add a bunch of red um, data points as well. So you have some red data points. So because I have some red data points now, I am going to rework my nearest neighbors. So the nearest numbers are not these ones anymore. But let's take this out. And yeah, let's add a data. So if I want to now get any point like this, and I want to predict which label it should be, whether it should be red or blue, what I do is take the k nearest neighbors of this point. So let's increase k because we now have more of them. We have reds and blues. So let's increase k to um let's increase k to maybe 6, right? So let's increase k to 6. So k is 6. So we are going to look at the 6 nearest neighbors. Typically k is normally more than this, right? But so let's just go with k is 6. So we take the 6 nearest neighbors. And what are the 6 nearest neighbors? So we'll start with this one. Oh, that's pretty big. Okay. So this is the first neighbor is red. The next nearest neighbor is also red. The next nearest neighbor is blue. The next nearest neighbor is red. The next nearest neighbor is blue, right? So how many neighbors is that? 1, 2, 3, 4, 5. So we're looking for 6 nearest neighbors. So where is the next nearest neighbor? Let me just take it to be this one, right? Okay, so we have 6 nearest neighbors. So from these 6 nearest neighbors, we will now calculate the one that has the highest number, which class has the highest number of members. Interestingly, in these 6 nearest neighbors, 3 of them are red and 3 of them are blue. So that's kind of a tie. But okay, let's increase it to 7 just for the sake of okay, tiebreaker. So what's the next nearest neighbor? If we wanted to add the 7, it's likely this one or this one, right? But let's just choose this one because it's easier to see. So if you look at this, and that's why typically when you want to do that, k has to be an odd number, I guess. So if you look at this, you have 1, 2, 3, 4, 5, 6, 7 nearest neighbors. So of these 7 nearest neighbors, 4 of them are blue and 3 of them are red. So that means the higher, if you go by votes, right, the higher number is what is blue. So that means we would classify this point as being blue because the k nearest neighbors, the mode is blue. So this is basically the simple principle of k nearest neighbors. So that's how that works. So let's look at this now. Um, Again, let's look at it. Choose K, which is the number of neighbors. So we started with 3, 4, 5, 6. We ended up with 7. Compute distance from query points to all training points. So from that point that we want to classify, compute the distance. So the distance is calculated like we say using the Euclidean distance equation. And when you calculate that, there's actually no training phase, by the way, for KNNs. The computation happens at prediction time. So when you compute the distance, you select the K closest points, right? Like we said. And when you select those K closest points, you now do the classification and pick the majority class. So like we said, in that case, the majority class was the blue class because the blue had 4 elements while the red had 3. If it is a regression problem, then you calculate the mean of the values from those K nearest neighbors. Right. So typically, when you are choosing K, if you choose a small K, it's always going to be sensitive and may cause overfitting because you are not you are not getting a representative number of elements. You are picking only the few, right? So it's always better when you are doing K nearest neighbor to choose a large K, right? So you get a smoother decision boundary. Now the distance matrix, the matrix you can use to calculate the distance when you are calculating the nearest neighbor is Euclidean distance. You can have a Manhattan calculation, Minkowski calculation. You can also use cosine similarity. Cosine similarity is a way of calculating for vectors. This is really for embeddings. We'll talk about that. This is very interesting. Like if you want to classify embeddings, and we can see how we can use this when we're doing embeddings. Embeddings are essentially representation of meaning, right, that are learned by neural networks. So we can use this to represent concepts. Okay, so that's K, that's how you calculate that. So this is a very simple example with Python, right? If you are using S, S, sklearn, right, you just bring a K neighbors classifier and you do that. And then you can do model.fit with the X and the Y values, and that's it. You do model.predict. This is a pattern that we use. But I don't think I really need to tell you the algorithm, at least from what I showed you on the screen, you can easily calculate that. It's very easy for you to manually implement K nearest neighbors. All you need to do is all of the data points, you would have to take the given point. You now have to scan through all the data points, right? And calculate the Euclidean distance. As you calculate the Euclidean distance, you put them in a sorted list, right? So when you've put them in a sorted list, when you finish calculating for all the data points, you now take the top X, the list X or list K, right? The list K, the values, the data points that have the list K in the Euclidean distance. And after that, um, you now find in that list that contains K, right? You find the class that has the highest number of members, and that is the class you will use to classify it. So that's how it is done. But of course, with sklearn, it becomes very easy. You just choose a K neighbors classifier, you specify the number of neighbors, and after specifying the number of neighbors, you specify the metric that you want to use to calculate the distance. So like we said, we have Euclidean distance, you have Manhattan, you have Minkowski, and you have cosine similarity. You can specify which one you want to use to calculate the distance, and it solves it for you, right? And with that, you can then predict. It's very easy. This fit is basically calculating distance for different points. So what are the pros and cons? K nearest neighbor is simply intuitive. You can, just that my explanation was enough to let everyone understand how it works. It's non-parametric, so you don't have to have any parameters. It works well with small data sets. Of course, when data sets are large, you can see that you are going to calculate the distance for every data point. So imagine 1,000,000 data points, you're going to calculate 1,000,000 distances, and then you are going to begin to filter to sort the million. If you do it optimally, you can be sorting as you're calculating when you're placing it into a list, and then you take, but it's definitely very slow. it naturally supports multi-class classification because you don't really need, if you have multiple classes, you just take the majority class, right? That's all from your K nearest neighbors. You calculate the majority. It's slow for large data sets. That's one of the cons, one of the disadvantages. That distance computation is the main thing. It's sensitive to irrelevant features. So some irrelevant features can just come in. Maybe just a single red dot in the middle of plenty blue dots, right? Will skew, could skew the prediction, right? It requires feature scaling. So you need to scale your features. Otherwise, remember, distance computation can become very big, just like gradient computation in the linear and logistic regression, right? So distance can become very big. That's why you need to do feature scaling. If your features are large, we are going to look at feature scaling on Thursday when we talk about feature engineering and all of that. So this example of feature scaling, you can use a standard scaler. So you create a pipeline. We're going to talk about pipelines as well, how to use sklearn to line up all of the things you want to do. But in this case, we're using a pipeline where we use a standard scaler to do the feature scaling first on the data that comes in. And then the next thing in the pipeline is the k nearest neighbor, right? Where you use a k neighbors classifier with 7 neighbors, right? And you do a pipeline fit. So pipeline fit will first do the scaling, and then it will now run the classifier, and that's it. So practical tips: always scale your features for k nearest neighbor. Again, because of distance calculation, which can become very huge. Remember, we're using squares. The Euclidean distance, for example, is using square root of squares. So if your values are large, it can blow up. Okay, use cross-validation to tune the value of K. So cross-validation, we'll talk about cross-validation later on when we do things like grid search and so on, how you can try different hyperparameters and then pick a model that fits based on that. And it works best when the data has clear neighborhood structure. So this is a pseudocode. I think we've already looked at this for K nearest neighbor. For each example in X train, compute the distance, which is the Euclidean distance, then you store the distance, right? That's all. That's the only training. The training is compute each and store for each, right? Um, for that particular X. Then sort the list based on distance label page. So you sort based on distance in ascending order. So the lowest distance will be at the top and the highest distance will be at the bottom. Select the first K items in that list, right? And then count the frequency of the labels among these K neighbors, like we said. So the one with the highest frequency, that is the label of it. That is your classification. So it's a simple algorithm. You have a Python implementation here, which we can also look at it later on. This is like you manually implementing it. So I can share this with you for you to study the code. You see that pseudo algorithm, compute distance, sort by distance, pick the k nearest neighbors, do the majority vote. And this is an example of that. Okay. So we will move on to we have dbScan, right? And then we have k-means clustering. I would really have loved to look at that. Let's see if we have enough time. Um, so for this, because of the time, we will just go very, very quickly through it. So we start with the k-means clustering. So when we say clustering, what is clustering? Clustering is an approach where you group data. It's called unsupervised training. You group data based on how close they are together. Sometimes it can actually even be mixed up with classification like this k-means, okay, which I kind of almost did that in the course of this class. But clustering is a way of grouping data together, that they have inherent similarity, right? Which may not be immediately um, apparent, right? But the clustering algorithm allows us to see that. So that's so there are two ways we normally do k-means, sorry, two ways we normally do clustering. We have what we call k-means clustering. So k-means is an unsupervised clustering algorithm. It partitions data into k clusters based on similarity, and it iteratively assigns points, right, to the nearest cluster center or centroid. So the goal of k-means is to minimize the intra-cluster distance, right, and maximize inter-cluster separation. I hope that is clear. So it's basically as you're training the model, right, the whole idea is that it is going to increase, right? It's going to increase the distance between the clusters while it is going to reduce the distance within the cluster. So the clusters will get smaller and smaller as time goes on, but the distance between the clusters will get bigger and bigger. So let me show you a good example of this, right? I'm trying to look for videos that will be, kind of just give you a very good idea of that. So if you look at this, it basically starts off, you see how clusters are, you know, um, this is the process of training, right? As you are training, clustering is happening, right? Clustering is happening, and clustering is happening. You see that it is things that are similar are coming closer together, and things that are dissimilar are moving further apart, right? And as the ones that are, uh, moving closer, they will tend to have the same color. So it's basically the same classification, right? And that's really just it. It's very easy to visualize, and it's also very easy to do that with sklearn. So this is just an idea of what it looks like. Okay, so it works best when the clusters are roughly spherical and well separated. Because of course, if you start off with a bunch of data that are very, kind of looking homogeneous, it becomes a bit difficult. The clustering doesn't happen, it doesn't spread out very well, right? Then So how it works is that you first of all start off with a number k. The k represents the number of clusters you want to have at the end of the day. Then you initialize k centroids. So a centroid is basically one of the data points that will form the center of the cluster. So now, or okay, a centroid may not necessarily be a data point, it might just be a point in space that you want as the center of your cluster. So what happens is you now assign each data point to the nearest centroid, the centroid that is nearest to that data point. So when you have done that, you are going to now recompute the mean of all the assigned points, right? So for each centroid, you have data points that you have assigned to it. Let me draw a sketch to explain this so that it will be easy to understand. So let's start off with again, just like we did with the k nearest neighbor, you have your X and you have your Y. Okay. Then in this X and Y, you have several data points. Remember, this is not a classification problem. This is clustering. So the data points do not have colors. We don't know whether they are red or blue or whatever. We don't know what their class is, right? But we just know that they are data points. We use clustering for unsupervised data sets, right? For unsupervised training. And what we mean by unsupervised training is training on data that is not labeled. It's not labeled. You only have the X values, the features, but you don't know what the Y values are, right? So we have a whole lot of these data points, scattered all over in this space, right? Now, typically, like they said, it's a good idea to use it where there is already some kind of, a bit of clustering. So you can see already that there's some kind of clustering in this, right? If you actually want to look at, if you squeeze or squint your eyes a little bit, you begin to see that there's some kind of clustering here, right? You can even see maybe 2 or 3 or 4, you know, uh, clusters generally. Like, let me see if I use different colors. So you can see that generally there's like a cluster somewhere here, and generally there is another cluster somewhere here, and generally there is another cluster somewhere here, and another cluster, somewhere. Let me use a different color. Another cluster generally somewhere here, and another cluster, you know, somewhere here generally, right? So if you squint your eyes, you will see, oh, okay, it does look like there are some clusters in those places. So with k-means clustering, what happens is that we first of all, to actually identify the real clusters, what we will first of all do is pick what we call centroids. So in each of these clusters that look like, you can actually start off with random points that you will call centroids. Of course, in k-means, you have to first of all decide how many clusters you want to have. That's the value of k. So when you decide how many clusters you want to have, that's the first step. Then when you decide this, how many clusters you want to have, then you can randomly select centroid. The centroid is the point where you want to start a cluster, like the starting point of the cluster. And you typically can just do it randomly. So let's say, for example, I can randomly pick, let's assume I pick 5. K is 5. I want to have 5 clusters. So I can randomly pick one centroid here, another centroid here, another centroid here. That's 3. Another centroid here, and another centroid here. That's 5 centroids. So now, you now get using the nearest algorithm, just like we did with the k nearest neighbors, we will calculate the nearest, for each data point, you calculate the nearest centroid to it, okay? So, of course, we'll use the k, any of the distance calculation, either Euclidean or Manhattan and so on. We just calculate um, the nearest centroid. So, for example, for these data points here, right? For this data point, um, so for example, let's say I want to calculate this data point, which I calculate the distance from this data point to each of these centroids, right? So I have 5 centroids. So I calculate the distance to each of these. Then when I've calculated, I find which of these centroids is closest to this data point. And I assign that data point to that centroid. So let's assume I had, instead of, let me just use different colors to, differentiate between the centroids, which is actually a thing. So I have a red centroid, I have an orange centroid, I have a blue centroid, I have a green centroid, and then I have a maybe yellow centroid. So I have those 5 centroids. So based on this algorithm of calculating which centroid that each data point is closest to, you will be able to see that all these guys here, okay, I did not do it very well. All these guys here will be yellow because they are closest to the yellow centroid. All these guys here will be yellow, right? Then all these other guys here will be green, right? And then so this guy will be green as well. So you can actually draw a line like this, right? This is the green line because this is the distance between, this is like the halfway point between the green centroid and the blue centroid. So these two guys will also be green, right? And these other guys will be blue because they are on this other side. So these other guys will be blue. We know these guys will be blue. And maybe even all the way up to here, right? Now, these guys will be maybe orange, right? Um, because these guys are closer to orange, so these guys would likely be orange. Um, and then red will be this guy here. So these guys here will likely be red. Right, so that will be your initial clustering. Okay, this guy looks like it should be blue, I think. So that will be your initial thing, right? But when you have done this initial clustering, right, that's not perfect clustering. So the next thing we'll do is we will recalculate the centroid. The centroid will be the mean of all the assigned points. And the mean of all the assigned points is likely going to land the centroid in the middle of the selected area. So that will shift the centroid a bit. So if we do that, the red centroid might actually shift from here to be somewhere closer to the middle. Okay, somewhere closer to the middle. So the red centroid might shift from there to here. The same way, the orange centroid might move from here to somewhere here, right? It won't be here anymore. The yellow centroid will definitely move because the yellow centroid, oh, I forgot. The yellow centroid actually captures these other guys. So maybe that's why I didn't have them. So I missed that, but the yellow centroid will actually capture these two guys. Okay, so they will be yellow, not orange. So with this, the yellow centroid would tend to go closer to this side where you have more of the yellow guys. The blue centroid would move as well, right? And move to somewhere here, and the green centroid will also move. Even though it has captured these guys and these guys, it may move to somewhere here. So when the green centroid moves to this point, now the centroids move. Then what happens? We will now recompute each point, whether they still belong to the centroid that they were before, based on the new location of the centroid. And what that may lead to is that some of the data points will shift to a different centroid because the centroid has moved, right? So some of the data points will shift. And it just keeps going like that. So that continues to be repeated. You calculate new centroid, then based on the new centroid, you reassign the data points to centroid again based on how close the closest centroid that it is. And after that, we recalculate the new centroid again. We continue doing that until we get to a point of convergence. The point of convergence is a point where the centroids do not shift anymore. No matter how many times you do it, the centroids do not shift. Either the centroids do not shift or the assigned points do not shift, right? Either one. You use some kind of error function to compute it. And the error function you can use could be either a mean square error or root mean square error. Any of these or a modular mean absolute error. You just use that to calculate how much the centroid has shifted or how much the data points. It's actually easier to calculate how much the centroid has shifted because you have less centroids. But if you want to calculate how much the data points have shifted, that you can still do that because you can keep track of the the data points, the assignments. So you keep doing that until you arrive at a value that is stable, and that is k-means clustering. So with that, when you get to that point where the values have have kind of um, you know, converged, then um, you have gotten your clustering done. Okay, so that's K-means clustering. Pros and cons: simple, fast, scalable. It works well for large data sets. Disadvantages: it requires pre-selecting K, sensitive to outliers, performs poorly on irregular or non-spherical clusters. Use cases: customer segmentation. So you can use K-means clustering for customer segmentation, for image compression, for market basket clustering, right? And document clustering. Customer segmentation, for example, if you have different customers, clustering is really good, right? When you want to determine preferences of people in a data set. So you just use the clustering and it will give you the number of clusters. It will give you the center points, the centroids of the clusters and everything, right? This might sound like it's a whole bunch of, theory, but it is very useful. DBScan is also similar, right? DBScan is called density-based unsupervised clustering algorithm. What this does is it groups data points that are closely packed together. It separates low density regions as noise or outliers. It does not require specifying number of clusters upfront and is great for irregularly shaped clusters. So key concepts: epsilon is a radius that you use to define a neighborhood, minimum points required to form a dense region. The core points are points that have greater than or equal to minimum points within epsilon. Epsilon is the radius that you use to define neighborhood. Border point, noise points. So the algorithm is that for each point, check if it is a core point. If it is, you expand the cluster by the density, reachability. You mark unreachable points as noise. So really, I'm not going to go into all of this because if I have to be honest with you, this is a whole lot of theory, right? It's a whole lot of theory. And I can already see that some people may feel like giving up, but what I want to tell you, don't give up. You don't really need all of this to do stuff, right? But it's just a good background. Okay. And I'm still going to double down on that point because I want you to get to that point where, don't worry, we'll get to neural networks, you'll even see, right? Okay, so advantages: it doesn't require K. You can find arbitrarily shaped clusters. It's robust with noise. Disadvantages: parameter selection can be tricky. It's not ideal for high dimensional data, sensitive to densities. Use cases for DBScan: geospatial clustering, identifying clusters of various shapes, and noise-rich data sets. So that's K-means clustering. Because we've kind of already run out of time, um, I'm going to I'm going to see if we can squeeze in the dimensionality reduction. But let me just leave us with this. Um, there is a place where you can look at dimensionality reduction. It's part of TensorFlow, right? Um, where you can actually see all of the different um I want to send the link and I want to just share with us uh, so that we understand all of this. Because the question you'll be asking is why do we even need all of this, right? Um why do I need to study all of this? It is good. Again, this is classical machine learning, right? These days people are talking about LLMs and so on. But for small amounts of data, right? These are very useful. You're not going to go and do deep learning. If someone gives you like a data set of 100 data points or 1,000 data points, you are not going to go train a model for that, right? So there are still a lot of use cases for these classical machine learning algorithms. Yes, and how do you know when to use? Well, I have the pros and cons here, which you can see. That can help, right? But one thing, if you're talking about um, when do I use in the same category, for example, clustering algorithm, you only have two that we've talked about, the DBScan and the K-means. And you can already see the pros and cons, right? So go look at this, right? And like somebody has said, you can try which one works best for the particular solution. It's good to do the hands-on. The hands-on is what helps you to be able to master it. So writing code is not difficult, right? Again, with sklearn, it is very easy. You can just so you can just import from sklearn. Uh, so let's say we have a this data set called make blobs, right? Then from cluster. So in the cluster sub we are going to look at sklearn itself, you know, like how do we how do we know where all of these things are? So we are going to look at that as well. So you start with k-means, right? Import numpy, then import matplotlib. Okay. So now let's just I'm just going to drop this code here so it's can just quickly because we are out of time. So you generate synthetic two-dimensional data X and Y true, right? Basically data that we want to cluster. Then we apply k-means. So to apply k-means, you just use the k-means function. You specify the number of clusters we want to have. So that's a k, right? So we have 3 clusters. How do you want to initialize the centroid? You either use random or k-means plus plus. So remember, it was mentioned here. You either use random or k-means plus plus. That's how you initialize. So then the random states you specify. Yeah. One of the interesting things to do, one of the interesting things you do when you are doing k-means is if you could look at how if you could look at how the clustering changes over time, that is okay. So I think by the way, what I would also advise, I think I've done this before, but let me do it again. Go and check out sklearn. They have a lot of stuff. You have demos. So this is an example. You have demos that you can look at, right? You can even go to their data book. So this is like a very good demo of k-means clustering on digits data set, right? And you can see it has done the clustering with the centroids here. You can go and run this code and see how it looks like. It also shows you how you can do visualizing. This is PCA, or well, this is reduced principal component analysis, which is for dimensionality reduction. So I would really encourage us to look at that, right? Um, yeah, so let me go back to Um, so this should be data sets and scalar dot cluster. So I think there were some typos. Scalar dot data sets. Okay. So so if we run this, you will see, this is how clustering happens, right? If we did not cluster, and let's see how it looks like if well, clustering is not, you are not really, um, remember it's unsupervised learning. So effectively what we are trying to do is to see how we have been able to identify the centers of the clusters. And this is how it looks like. So I'll pause there because we are out of time. Again, these are very interesting tools. Yeah, it's not as interesting as neural networks, which we will cover next week, but these are interesting tools for us to at least understand and know how to use. And sklearn definitely provides you with all that you need. So again, one last time, I will encourage everyone, go check this out. I don't know if we'll have time to look at dimensionality reduction, but that's a very important, it's even part of, it's important for feature engineering. So maybe we'll look at that in the context of feature engineering. We'll look at dimensionality reduction using PCA, and then that will be it. Okay, is neural network easier? No, it is not easier. Everything, it's tough, especially for neural networks. It's really understanding the architectures, right? The maths is the same. You won't see a lot of the maths, but neural networks are very sweet. Let me just put it that way. I can't wait till we start, next week. I started off with neural networks, so neural networks are sweet. They do a lot of interesting stuff, but all of these also do a lot of interesting stuff. So, um, I want to encourage everyone. Don't allow this to chase you away. This is what makes machine learning machine learning. So I'll stop recording.